And here we go. What you see in front of you on this worksheet are the 6 different types of starting points that we'll be using this unit. Okay? 6 different types of functions. When we looked at the worksheet from yesterday, we worked primarily with x squared, and we saw what happened when you added, subtracted, multiplied, and divided x squared with different numbers. Okay? X squared is one of those types of functions. And you can think of this as the original quadratic. And what we are going to learn about this unit is we're really going to dig in and classify what happens when you add, subtract, multiply, and divide different numbers to a quadratic, x squared, or a cubic, x cubed, or just a plain old linear, plain old x. Okay, now we could go higher, x to the 4th, x to the 5th, and so on. As it turns out, you really don't see a lot of new behavior. X to the 4th acts really similar to x squared, x to the 5th acts really similar to x cubed. So we're not going to go any higher than x cubed. Also, we've got to stop somewhere. And then, square root and cube root, and then absolute value. Okay, these are the 6 different types of functions that you spend the most time with. There are others, and we'll actually look at some others later on in the year. But these are going to serve as our starting points. Okay. Now, just to kind of give you a vision as far as where we are headed, by the end of this unit, you're going to be able to look at something like 2 times x minus 1 cubed plus 3 and analyze what's happening here and generate a graph without having to do the grunt work of picking a bunch of x's, plugging them in, getting a bunch of y values, and plotting those points. Okay, the aim for this unit is to shortcut this whole process by understanding how these different operations affect, in this case, a cubic function. And as it turns out, these different operations, as we saw yesterday, always behave in predictable ways. And so it really doesn't matter what the underlying function is. Okay, so this is where we are headed. It starts here with these 6 elementary functions, also called parent functions. These are going to serve as our starting points. Okay. Now, I'm about to contradict what I just said, because what I just said was we want to try to shortcut this process of picking a bunch of x's, plugging in, getting y's, and plotting points. We still have to do that. The difference is we're going to do that once today. Today is the day where for each function, we're going to pick some x's, plug them in, get some y's, and plot some points. The difference is we're going to do this once today. And the work that we do today, we're going to use throughout the rest of the unit. So that today is the day where we do a lot of plugging and chugging. We also do it on what happens to be the simplest version of every type of function. Plain old x squared, plain old x cubed. But after today, we're going to stop plugging in a bunch of x's because we will have already done that to the elementary or the parent version of each function. Okay, now I've talked this up enough. Let's spend some time with x squared. So let's suppose that x, let me zoom in here. I don't have a keyboard, so I have to use the slider. There we go. Let's suppose that x is negative 2. What is negative 2 squared? Thank you. 4. How about negative 1 squared? 1. How about 0 squared? And then 1 times 1 is 1. 2 times 2 is 4. This is the only time this unit we will plug and chug on x squared. From here on out, we'll use these 5 points, which we will refer to as anchor points, as part of our analysis for what's happening with any quadratic that we look at. Okay. Now, if we've gone to the trouble of plotting these points, we might, or of generating these x and y pairs. This is a y value. We might as well plot the points, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. We might as well plot the points. We might as well connect the dots. Oops. And we see the that traditional U shape that we see with every quadratic. All right. While we are here, what is the domain of x squared? Now, there are 2 ways we could answer this question. We could look at the graph, take our pencil, hold our pencil over here, and ask ourselves, are we touching the line? And the answer is, are we touching the line? Yes, because of the arrow. This arrow is pointing up and to the left forever, so over here on the left, we are touching the line. As we move to the right, we keep touching the graph. We touch the whole time. There are no gaps and no jumps. Therefore, the domain is all reals. Tell your neighbor what the range of this thing is going to be. Now, if you're a little fuzzy about range, hold your pencil down here. Ask yourself, am I touching the graph? You're not. And then at what point as you move up do you start touching the graph? So guys, what is the range of x squared? Where does it start? Mac, what do you think? 0 to what? Infinity. Very good. We start touching on the graph itself, so it's a bracket, 0 to infinity range. So domain is all reals, range is 0 to infinity. I'm going to pause my recording for just a second. What I want you guys to do is repeat everything that we just did for x cubed. Okay, so plug in these 5x values, get the matching y values. Okay, if you have a pen, maybe pump the brakes on plotting the graph for just a second to make sure that your points are good. But I'll give you like a minute. All right. So, Morgan, when x is -2, what is x cubed? -8. Good. Matt, when x is -1, what is x cubed? -1. Nate, when x is 0, x cubed is? It's the easy one. John? Sage, when x is 1, x cubed is 1. Franny, when x is 2, x cubed is 8. Okay, so these are our anchor points for x cubed. If we plot these out, -2, -8, 1, 2, 3, 4, 5, 6, 7, 8. -1, -1, 0, 0, 1, 1. And then 2, 8. 1, 2, 3, 5, 6, 7, 8. Right there. We see the traditional S shape of x cubed. X squared has a U shape. X cubed has an S shape. Tell your neighbor what the domain and range of x cubed are. Yeah. Say it again. Yeah. What is the domain of x cubed? Brennan, what do you think? Well, these arrows point left and right forever. Well, let's look at this differently. Do you see a square root? Do you see a fraction? So it's all reals. Okay. If you're looking at the expression, our two big red flags are fractions where there's a variable in the denominator and square roots. Okay, if we don't see either of those, it's all reals. From a graphical point of view, if we hold our pencil over here, we are touching the graph because of the arrow. Make sense? Okay. So domain is all reals. How about the range, guys? Yep. Also all reals, or negative infinity to infinity. Either one is fine. I prefer just to say all reals because it's a little faster, but writing negative infinity to positive infinity is 100% okay. Now, let me give you a word of caution. You are going to have to know all of the anchor points for all 6 functions, okay? Because these anchor points are going to serve as our starting point for every function that we look at. If you look at x squared and x cubed, there are some things that you can figure out about the anchor points that will help you memorize them. The first thing is the x's are just -2 to 2. And the y's are whatever you get when you plug -2 to 2 into the elementary function, into plain old x cubed or plain old x squared. And that's a pattern that we see repeated down here with x and absolute value. Absolute value, the x's are once again -2 to 2, and the y's are the absolute value of -2 to 2. Speaking of, what's the absolute value of -2, guys? 2. Absolute value of -1? 1. 0, 1, 2. Graphing these out, we see the V shape of an absolute value. Landon, what's the domain for absolute value? All reals. All reals. Absolutely. Domain is all reals. Oops. Okay. Mike, what about the range? 0 to infinity. Very good. So as you're memorizing these anchor points, for a lot of these, the x's are just -2 to 2. If we look at our linear function, I have -1 to 1 because this is a line. You really only need 2 points. It really helps us to get a good line if we had 3 points. Okay, so because this is just a line, I just have -1 to 1. If it helps you to just have to shove less things in your brain, there's no harm in having these x's run from -2 to 2. There's no harm with having a couple of extra anchor points. You only need -1 to 1. -1, 0, 1. Whatever x is, y is. Okay, so what I said about x being from -2 to 2 can still apply to the line. It doesn't need to because it's a line. It's only 3 points. You only need 3 points to get a good line. But if you had a couple of extra points on your graph, that's just fine. That's fine. There's no harm in that. zoom in just a smidge and get out my ruler. Give myself a good line. Shoot. Try that again. That's a terrible line. It's very hard to draw straight lines on this thing without using the line tool, which to me feels like cheating. That's better. So here's our line. It's green because I forgot to change the color back, and I don't want to have to draw this line again, so we're just all going to live with it. Domain and range of this guy. It's all reals. All reals. All reals. So for these four functions, if you're trying to learn the anchor points, the x's go from -2 to 2, or they could go from -2 to 2. And the y's are just what you get when you plug -2 to 2 into the elementary function, into the simplest version of each function. Plain old x, plain old x squared, plain old x cubed, plain old absolute value. Our last two functions are roots, square root and cube root. Because these are roots and we want them to work out evenly, we choose x's that are either perfect cubes or perfect squares. Okay? Because these are roots, I can't do -2 to 2, especially in the case of square root, because I want my x's to work out evenly, / at all. So for square root, I pick x's that are perfect squares. Square root of 0 is 0. Square root of 1 is 1. Square root of 2, or of 4, is 2. Of these 6 graphs, the graph for square root is, to me, the most interesting, because this is the one graph that has a definitive starting and stopping place. Square root begins or ends at 0, 0. There is nothing over here to the left that we graph. It winks into existence at 0, 0, and then it slowly makes its climb upward. Actually, if I want a really accurate graph, oops, I should cross at 9, 3. There we go. Worth it. Shoot. Try this again. What's the domain of this function? And note, this is different because the graph doesn't go on forever in one direction. It goes on for forever in the other direction, but not in both. So my domain is what, guys? Kyle, what do you think? 0 to infinity. Yep. How about the range? Pretty much the same. All right. I'm going to give you guys another minute again. Come up with the points for cube root. Okay? Harrison, what's the cube root of -8? It's -2, yeah. Yeah, because it's cube root, negatives work just fine. Square root, there's a bunch of drama, but cube root handles negatives just fine. Okay. Cube root of -1 is -1, 0, 1, 2. Fun fact, if you take the anchor points for cube root and you exchange x and y, you get the anchor points for x cubed. Because these two functions are inverses. They undo each other. That's a discussion for another day. Plotting these out. 1, 2, 3, 4, 5, 6, 7, 8. -8, -2. -1, -1. 0, 0, 1, 1, 2, 8. Shoot. Fix that. There we go. The graph for cube root. Domain and range is once again all reals. This thing extends up and down, left and right forever. And these, my friends, are the 6 elementary functions or parent functions that we are going to look at and use in this unit. And you do have to know anchor points, domain, and range. It also helps if you know the general shape of each graph. So that when you're doing a graph, you know what to expect. But you do have to know anchor points, domain, and range for all 6 of these. Okay. Now there is a rhyme and reason to the anchor points for x squared, x cubed, and absolute value. The x's can just run from -2 to 2, and then the y's are x squared, x cubed, absolute value of those x's. For the roots, you need to choose the first few x's that work out evenly for square root or cube root. Okay. As far as domain and range goes, this is where being familiar with the general shape of the graph helps. For all of these but square roots, the domain is all reals. And for half of these, the range is all reals. For the other half, it's 0 to infinity, depending on the shape of the graph. And this is where knowing the shape helps. Okay. Now, I am going to talk more about this in video 42, but to give you a preview, the reason why you need to know these anchor points is they provide your starting point. Let's go back to this example that I talked about at the beginning of the lesson. If we wanted to understand what was happening in this function and graph it, our starting point would be to realize, clear this out a little bit. Our starting point would be to realize that this is a ginned up version of x squared, or of x cubed. This is x cubed with some different transformations in place. And so we would start with the anchor points for x cubed. Because this is a version of x cubed. We would then apply the transformations that we see to the anchor points. For example, this 2 multiplied out in front tells us to multiply all of the y values by 2. Okay, this plus 3 at the end tells us to add 3 to all of the y's as well. So these anchor points undergo some pretty dramatic changes. This is where we are headed. So I want you to keep this in mind as you start to learn these anchor points. Okay, and as you watch video 42 tonight. Okay? All right.